Example problem 4. Here we're given that we have a sample of atomic oxygen. So atomic oxygen at 300 Kelvin. I'm not sure how you get that, but I'll leave that up to some bright chemist. And the question is, what proportion of atoms are in the first excited state if it lies 1,000 kilojoules per mole above the ground state? So I've got a system, presumably an atomic system. Here it doesn't really say. And for atomic system, anyway, we'll treat it as an atomic system. And so for those, E1 is the ground state, and the first excited state is the first energy level above that, which I'll denote here by E2. So those are the energy levels. And what we're given is, in this one, that E2 is 1,000 kilojoules per mole above E1. So if I take E2 and subtract E1, that's got to be equal to 1,000 kilojoules. And we need to get that into just energy. So 1,000 kilojoules, 1 per mole, and a mole is just Avogadro number of atoms, in this case, oxygen atoms in this case. And we know what Avogadro's number is, which I represent by N sub A. And it's 6.022 times 10 to the 23rd atoms in a mole of atoms. And if I divide this out, remember kilo is 10 to the minus 3, and so we get in this division, when I put it in my calculator anyway, I got 1.66 times 10 to the minus 18 joules. So on the atomic level, the state energy E2 is 1.66 times 10 to the minus 18 joules above the ground state E1. And that's, what is that? That's roughly 10 electron volts, something on the order of that. So it's actually a fairly reasonable number. And now then we just have to remember the Boltzmann probability distribution. Here, remember, I'm using capital P's for probability. So here the probability of a particle being in the ground state is P1. Probability of particle being in the atom being in the first excited state is P2. And remember, the probability can be represented, at least for a large system, is the number of particles in that energy level, N1, divided by the total number of particles. And the number of particles in state 2 divided by the total number of particles, again, is the probability for being in that state. And those are just equal to these probabilities are just equal to this Boltzmann factor. P1 is e to the minus E1 over KBT, and P2 is e to the minus E2 over KBT. And what I'll do is I'll take these last equalities and form the ratio N2 over N divided by N1 over N. And N2 over N I know is this Boltzmann factor here. And N1 over N is this Boltzmann factor here. Divide the N's out, and I get the ratio of the number of particles in the first excited state to the number of particles in the ground state in this particular problem, which was at 300 Kelvin. We've calculated the energy difference. That was the 1.66 times 10 to the minus 18 joules. And we were given that it was at 300 Kelvin, so nominal room temperature. And, of course, the Boltzmann constant, which I represent as Kb, and most books just simply K, 1.38 times 10 to the minus 23 joules per Kelvin. Notice the units go out. It has to. Anything that's raised to a power, an exponential raised to a power, has to be dimensionless up here. When I calculated this, I got minus 401, and my calculator did that fine. But then when I tried to plug into my calculator, and you may have a better calculator than I do, this e to the minus 401, well, it didn't give me an answer on that one. So what do? We need to have a numerical value that maybe is in a more recognizable form. You go to your boss and say, well, the number is this, and unfortunately your boss is an MBA, is a business major, and he doesn't know what the natural exponent is, although he does know power of 10. Okay? So let's convert it to a power of 10. And it's actually fairly easy. What I'd like to do is I'd like to find what E is, what power of 10, what do I have to raise 10 to get E. And if I take the if I take the log base 10 of both sides, then the log base 10 of E, log base 10 of 10 to the x is just x. That's what we mean by the log base 10, it's the exponent. And so what that says is, if I rearrange this, is that x is this value, and so I plug that value in up here for x, and I get that the natural exponent e is equal to 10 to the log 10e. Basically, these are inverses of one another. Raising to the 10 power and take the log to the 10 power. Well, I'll use that. So I'll use this relationship, really from logarithms, plug that in for e here. So e is 10 to the log 10 base e. I know that the 10 to some power to another power, I just multiply this times the power. So I use the properties of logarithms to get to there. And then this value I can compute. It's, well, log 10e is 0.434 when I did my calculator. I need to multiply that times minus 401, and I get minus 174 to the 10th. Well, that I can't evaluate that. If I try to take 10 to the minus 174, well, it doesn't give me an answer either. But the value of the ratio of the number of particles in the first excited state at 300 Kelvin to that in the ground state is a very small number. So almost all the particles at this, or all of the, in this case, the atomic oxygen, almost all of them are in that, but a very small number are not.